Okay, so we worked on this topic, which is the development of a cooperative work method based on autonomous learning of implicit instructions, and it's aimed at wearable robotics. So our lab actually developed this wearable robot arm, and we aimed at being able to multitask with it in any environment, whether it be construction site, like you can see on the video, or daily life situations. And one of the main focus was to have this low cognitive load when operating the robot arm, which means that it doesn't require as much attention as you would think it would. So right now it's operated essentially using this glass type interface with a face vector where whichever that face vector is pointing at, the arm understand that's a target point, and that's where it has to either grab or aim its end effector to, which reduces the number of parameters and is kind of a natural user interface such as voice or just a simple operation method. So it allows for cooperative work and mutual adaptation, as in the arm understands what the user wants it to do, and the user can also correct the behavior of the arm depending on how the arm is behaving. So we were aiming at constructing a more intelligent system rather than that which is really mechanical, which would understand intention of the action. And we based our research on the clever hands effect, which is basically stating that intention estimation can be done through cues and motion that are embedded in action. So if you are going to stand, you are inadvertently going to have those slight cues that are embedded in your action that would allow the system to understand what your intent is before you actually perform the action, and use those cues embedded in the motion of a person to build an intelligent learning system. So just based on deep learning, and which would be able to use those cues to instruct a command to that robot arm before you would actually have to physically or vocally express it. So it would be a new learning methodology which would allow action to be interpreted before even making that command. So a little bit more on the background is that right now, in terms of cooperation between machine and human interaction, there's a lot of research that focuses on robot autonomy, and the robot and the human, while working together, they each perform their own task and then collaborate on it. But there's very little of a robot and a human actually working together on the same task because of how their workspace would actually overlap and dangers that that would imply. And there's a lot of issues related to that. But we actually tried to focus on that aspect of multitasking and using the robot as a way to perform a task that a person would not be able to do alone, such as when you're typing and you still want to continue typing with both hands, but want to grab the phone that's ringing, something like that. You would use the robot as a way to expand your own workspace instead of having the robot perform its own task and you your own task, and then like put the results together and see that improvement. So that's the idea behind the concurrent task, which is being able to do something that would otherwise require you to stop your own action, or that would require two people to work together to be able to achieve that same thing. And it's combining the flexibility of the robot arm with the human's judgment and able to expand that person's behavior. And that interface still has to be low in cognitive load, because if it's requiring too much of your own attention to operate the robot, then it loses the purpose of using the robot to expand what you would be able to do on your own otherwise. And related research usually pays attention, when they pay attention to those implicit cues, they still separate that, or well, this is the English version, the robot data and the human data. So it's, for example, either you use explicit ways to instruct the robot. So, like you would see an electric door with a button, and you would push that button to have the door open. You need to explicitly instruct the robot what you want it to do. And then you use the input output information, which increases for every new instruction. So every time you want a new action to be performed, you would increase the number of input data to a specific system. Whereas ours focuses on implicit instructions, such as an automatic door, which is programmed to open on its own as a person approaches. So the person doesn't have to instruct anything. And the problems with the conventional methods, or methods that are currently used when they try to deal with this idea of having a robot perform something without actually instructing it to, is that they would build static systems. So for each specific action, there would be a specific model. So you would have high task dependency, and you would need to build that model for every single action, which would be very time consuming and difficult to adapt to any environment because of all those variables that you would need to input and specify for every single action that you would want to be doing with a robot. Whereas, so it focuses on that clever hands effect. And this is the idea, is that you can input a specific number of commands and then use the same system to have the robot perform several actions. So if intent is understood, and you take the idea that there are, for example, we used 6 different input commands, and there's a wide variety of different actions that from those 6 commands a robot would be able to perform. And so that would limit the number of inputs, and then you can have the robot arm adaptively learn from its own experience, and as you continue to use it and rectify the behavior, that dynamic system is able to adapt. So we have a combination of an implicit and explicit interface, and the idea is that in the first step, you would actually use verbal commands to instruct what the robot arm should do. So for example, you're turning your head and you actually voice the command, which would be to take the water bottle. And using speech recognition and that part of the system, the robot is able to understand what it has to do and understand the relationship between your motion and the voice command that was instructed. And in the second step, it's able to associate those motion patterns with that command. And the next time you would actually want it to take the bottle, you wouldn't need to voice the command. It would understand the action that is expected of it solely by the motion of the user. And in order to do so, we decided to use as little sensors as possible because we wanted a minimally invasive system. But to have motion data, we would have that face vector that is used to indicate the target to the end effector. And we would have IMU sensors at the wrists and the chest area, the torso area, which would not be in overlap with the wearing mechanism of a wearable robot arm. And we would need minimal perceptual discomfort for the response of that robot arm. And the fact that we wouldn't be using a camera and information related to the environment would mean that the robot would be as little as necessary dependent on that task. And we would not be putting any information related to the task or the environment to make that system really independent from those 2 elements and be able to use it as any context or as much as possible. So this is the design system. So as I said before, these are the input data would be those IMU sensors that are placed at the wrist area, the chest area, and the phase vector, the glasses. And then we would use the joint angles from the motors and motor encoders. These, along with the labeled command, are inputted into the neural network as motion data and all the input data related to it, which would then use classification to be able to find which action among 6 different labels that we priorly set was the most likely to be the instruction intended by the user. And through the learning process, the next time the person would perform similar motion, that user wouldn't need to voice a command. The robot arm would just understand the action because of the motion of the user and just automatically perform that command that it would understand was the intention of the user. And this is possible because we base this idea that there's a certain continuity in human action. So, for example, if you're sitting down, there's only a certain number of action that one would expect to perform next. So, for example, you're sitting, you would then either stand or lay down, or there's actually a limited range of possible action that you would expect the person to do. And that's the same logic that the system is using. So given that you just perform this motion, there's automatically a whole range of other motion that would come next that are eliminated. So it reduces the possibility of commands that you would actually want that robot arm to be instructed. So these are the 2 steps. So first, you would use that voice command for labeling, but then the next instance of the same action, you wouldn't. It would just automatically reach for whatever you wanted to reach. So the interface is designed like this, using input data. So as I explained, the arm angle and the IMU data, and then the output is the instruction label out of 6 different possibilities that were set priorly. And then we have a CNN layer, so 2 different neural recurrent networks, one for robust feature extraction and the other for its memory capabilities, and also for the temporal feature extraction and complex patterns. And when we compare with other related research, one of the differences is that we are using both the data from the robot arm and from the human, so from the user. So it actually, that idea of relationship and interaction between the machine and the person and that human machine interaction, it's actually embedded within our system. Even the system is focused on that idea of interaction between a person and the machine. And it uses data from both elements in order to be able to understand how these interactions coexist and how the action of one affects the action of the other. So it's actually that collaboration is fully integrated in the network and in the software aspect of the system. So this is an example. So in the first instance, we have explicit instruction operation on the left, where the person was actually voicing at the beginning, and then next time they were actually performing that action, the robot is able to perform the same task without being instructed vocally any commands. And the bottom is how the interface is labeling with all those different commands that are available to it. So before learning, there's use of voice, and then after learning, there's only motion data and no need to explicitly instruct any commands for the robot arm to perform an action. And adaptive learning means that the robot and the person actually adapt to each other. So in case of error, there's intervention from the user. So if, for example, on a failure case where the action is not executed, the user can actually voice that instruction and the robot will perform it, even if the interface hadn't priorly detected that command. And this instruction is automatically stored in the system, and the robot is able to learn its mistake, and just the next time it will be able to correctly detect that instruction. And then in case of incorrect labeling of the task, meaning that the robot would perform the wrong action related to the user's motion, then the user is able similarly to stop the robot and voice the correct command. And this is also stored in the system, and it would actually allow the robot to learn from the mistake once again. And the next time this identical type of pattern would occur, the robot would not make the labeling mistake and would perform the same action. So it's allowing the machine to make up for its own shortcomings with the help of the individual. And the person is able to also gain an awareness of where the machine is still lacking and how to pay attention, or which instances should actually pay attention for the next time it wants the same task to be executed. And as verification tests, we performed two types of trials. So one was autonomous learning of the system. So how is it able to understand and comparing the accuracy and the task execution of the robot with respect to if we were using voice commands. And then also, how will that cognitive load, how does it affect task performance, and is it really beneficial for the user to not be using those voice commands and to be operating a robot solely based on his own motion data, and does he perform as well if he is multitasking with the robot arm as he would if he were without, or such parameters. So this is the idea that we use. We would use on day one, we would perform one task for 10 minutes with voice instructions. And then on day two, the same person would perform either the same task or a different task with, again, voice instruction, or this would be selected randomly, or using solely the motion data without voice. And then same thing for day three, and depending on whether the previous day they use the voice instruction, they would be using this time only implicit instructions, and vice versa, to be able to compare task performance with the two methods. And so to verify task dependency, this was the task setting. So we would have the robot arm, and then a task area, and then the sensors as explained previously, and training data was divided as so. So these are the type of tasks that was used to test the cooperation method. So we would have different tasks with different numbers of labels and parameters. So it would range from 3 to 4. These were always performed in the same order. So for example, the first one reaching, then wiping, and then return, or the second one grasp, reaching, release, return. They would keep the same order. And then the last task, the task number 4, was the only one that would be executed with labels from which the order would be changing. So the robot doesn't actually know which action comes next. And that's the one that was the most challenging, which can be seen in the results. We can see that as the number of labels increase, also the accuracy would be decreasing. And one of the main reason for this is that we were using the same model for all tasks. So it may seem lacking accuracy as task becomes more and more random in terms of which action follows which, but that's also because we specifically chose not to redesign the model from one action to the next. So it becomes very loaded information, and becomes very difficult to sort information and to be able to accurately recognize those patterns, because those patterns become more and more difficult to see. And this can be seen for task 4, where there's a lot more mislabeling compared to on task 1, where there's only 3 labels and they're always kept in the same order. So this is a discussion related to those results, which means that while the system was successful in estimating those methods during tasks, and while the accuracy was decreasing, it was still suggesting that there was this low task dependency, because it was still able to perform about 79% of correct labeling on average, which is, even though it is a considerable decrease from a regular task, which would be 3 labels always kept in the same order, which would be an accuracy of 93%, it's still higher than previous comparable models that we found. And as task complexity is increased, it was expected that accuracy would decrease. And that's maybe related to the fact that we haven't yet considered using context in terms of finding out those patterns, and the system isn't fully aware of that relationship between the action more than the relationship between the motion and the robot's behavior. It's not actually learning to recognize a task and be able to know the context of what it's actually performing. So the second main focus of the test was the accuracy evolution, along with how the cognitive load was comparable between performing a task with explicit commands and with implicit commands. So to do so, the user would, here's an example with task 3, where the user would use explicit commands for one day, and then either explicit or implicit commands, and would then verbally explain how using either one of those methods was actually preferable to the other one, or his feeling with respect to using those 2 methods. So this is the task 3 with all the patterns and the layout of the task. And we perform both quantitative and qualitative evaluation. So quantitative evaluation was done with task performance and accuracy, and for multitasking, the person would, with its main task, be performing, as can be seen in the video, the handing over of the dust cloth and the cooperation with the robot. And as a secondary task, the auditory oddball, which means recognizing a specific sound. So the person is hearing different sounds, and it has to recognize when one specific is being heard. And we tried the accuracy for that to be able to see how well it was performing. The user was able to perform on both tasks while only using implicit instructions. And then the qualitative evaluation is done with the NISO TLX task, which means that the person is answering a survey, and using those 6 skills, we're able to see the person's opinion on the use of the developed method. For accuracy evolution, these were the result that we obtained. So from day 1 to day 2, there was a visible decrease in accuracy, which we assume was probably related to the sudden switch between the use of explicit instructions and implicit instructions, because day 1 is exclusively voice command, while day 2 is exclusively motion data, or, well, it's randomly determined, but so for 50% of cases, it would be a sudden switch from one to the other. And since the model wouldn't be redesigned in between those 2, there was a chance that that was where that discrepancy was coming from. But then from day 2 to day 3, there was a significant increase in that accuracy in estimation, and showing that between day 1 and day 3, the accuracy is about the same, while the operating method is completely different. And regarding the task load evaluation with the nicety LX score, we can see that whether it be performance on the secondary task or that task for evaluation, while from day one to day two, results between use, whether it be voiced instructions or implicit instructions, were relatively comparable. They were about the same. Starting by day three, the load score, so meaning the attention requirement that the person would need to be able to operate a robot while performing its independent tasks, along with the performance of the user on that secondary task, were different, considerably different, showing a decrease in that load score, meaning that they would actually need less instructions when operating a robot using only motion data, so they wouldn't need to actually pay attention to the robot operation and would just be doing their own task and assume the robot is doing whatever they expect it to do. And they are therefore able to pay more attention on that secondary task that they're doing on their own and perform better than if they have to also think about what instructions they have to give to the robot. So those are the two main points that we took from that experiment. So the accuracy, although at first it seemed to worsen, it actually showed us that there were no significant differences between either operation means and a person is able to perform better on a secondary task and not, therefore, not that's related to not paying as much attention on that robot operation. So we can have as good accuracy on a task execution with way less attention and therefore less demand for the user. And this shows that we were actually able to develop a method that would have lower cognitive load demand with a better performance at multitasking. And as a conclusion, these were the results. So we were able to propose the constructed cooperative method interface with those implicit instructions and have about 86.4% estimation accuracy on 4 different tasks, which means that the model was actually very little dependent on that design method because the model wasn't redesigned between those 4 different tasks. And those accuracy improvements between implicit instruction from one day to the next suggests that as the person gets used to operating the robot, it is able to just solely rely on the effectiveness method and therefore pay less attention and therefore focus on their own action, which also means that while you would before pay attention to the robot and therefore maybe have less accurate movements, or your motion data would actually be kind of loaded with discrepancy because you aren't moving as smoothly as you would if you were actually used to operating a robot at the same time as performing an action. As you get used to it, you just pay little and little less and less attention to that element and just resume moving as you would in your normal daily life, whether there'd be a robot or not. And this means that that allows for less attention and therefore lower cognitive load. And then as future work, we still plan on comparing that IMU data sensing type of motion acquisition to other means such as motion capture or images, because deep learning is very demanding in terms of data that is needed. We still need to compare that with other maybe more efficient ways of collecting data. And then optimally, we would have autonomous management of experience and of learning data, because that would allow the system to have better memory element and therefore be less likely to, as with continuous use and increase in data in the system, that would be less likely to lead to worse result because of that storage capability and management capability. So this is our research, and thank you for attention.
Okay, thank you so much, Lena.
Thank you.
Okay, what time is it over there?
It's almost 4 a.m.
Okay, that's right. And then we do not have much time this time, so like I will pick just one question. I apologize for everybody else. You got so many questions, but I just cannot. So I will take this one. Wiping tasks. So the human user having to control his emotions cannot come to the helm being grumpy, cannot laugh or do any other task at the same time as some do. Can this say something about our required mental states in the future?
Well, actually, we're only using motion data, so yeah, the emotion element of the person. Well, yeah, the emotion element of the person right now isn't really taken into account since it's only motion data, but it's true that depending on the person's mood, the way they move may be impacted. So it may be an element that has to actually be taken into account later because right now it's so yeah, if you're grumpy right now, if you're grumpy and that changes the way you would actually move, the system would actually be confused by the operation probably, but we're not taking it into account right now, so I'm not sure.
I guess this is still a first step.
Yeah, it's still a
Yeah.
first step right now. It's
Yeah. Okay, well, thank you so much.
yeah, thank you.